Good morning, everyone. This is Dr. B. Haribabu, Assistant Professor, Department of Mathematics, Pace Institute of Technology and Sciences. Today, I am going to give a lecture on Hasse diagram. So, let us discuss about Hasse diagram. Before we are going to discuss Hasse diagram, let us see some definitions. First one is partially ordered relation. Partially ordered relation. Let capital P be any set and R is a relation on P, then this R is said to be partially ordered relation on capital P if it satisfies three properties. First one is reflexive. So reflexive means for all elements A belongs to capital P, ordered pair A comma A belongs to capital R. So reflexive relation means for every element of P, set of all ordered pairs with the same elements A comma A belongs to R. Next one is antisymmetric. Antisymmetric for P whenever A comma B belongs to R and B comma A belongs to R, then both are equal. So that means if any two different elements we take either A comma B belongs to R, then B comma A does not belongs to R. The reverse ordered pairs does not belongs to R. Then that property is called anti-symmetric property. Third one is transitive. Transitive. Third property, transitive. For any three elements ABC belongs to capital P, whenever A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. So transitive property means for every three elements A, B, C belongs to P, whenever AB belongs to R, BC belongs to R, then AC belongs to R. So partial ordered relation means a relation R is said to be reflexive, antisymmetric, transitive. So then that relation is called partially ordered relation. So next, covering of an element. Covering of an element. See, we have three different type of partial ordered relations. First one is less than or equal to, and second one is subset, and the third one is divides. So we have three types of partial ordered relations. So first one, when you take P is equal to set 1, 2, 3, 4, and then P comma less than or equal to is a poset, is a poset. So what is a poset? Poset means a set together with a partially ordered relation on that set is called a poset. A poset means a set together a partial ordered relation on that set is called a poset. So this is the denotion of the poset. So P is equal to 1, 2, 3, 4. Then P comma less than or equal to is a poset. So which means here less than or equal to is reflexive, antisymmetric and transitive. Now covering of an element. So which means if x less than y and y covers x, y covers x. If, which means there is no z belongs to P such that x less than z less than y. So y covers x means if x less than y and there is no z belongs to P such that x less than z less than y. So when we observe here, first we fix the first element, then the next elements we check whichever the elements are covered the first element are. So 2 covers 1 or not. So clearly 2 covers 1 because 1 less than 2 and there is no other element such that 1 less than that element less than 2. So 2 covers 1. Next one, 3 does not covers 1 because 1 less than 3, okay, but there is an element 2 belongs to P such that 1 less than 2 less than 3. So which means 3 does not covers 1. So next one, 3 covers 2, 3 covers 2 because 2 less than 3 and there is no other element between 2 and 3. And next 4 covers 3. So 4 covers 3 which means 3 less than 4 and there is no other element between 3 and 4. So this is one type of relation less than or equal to. When coming to the subset relation, we take capital A is a finite set A comma B and then power set of A comma subset is a poset, is a poset because subset is a partial ordered relation. It satisfies reflexive, antisymmetric and transitive. So P of A means set of all subsets of A. That means first empty set and singleton A, singleton B and A comma B. So this is P of A. Now we observe that, so first we fix the first element empty, then from the next elements we observe that, so what are the elements are covered? Pi. So clearly singleton A is covers pi, singleton A covers pi because pi subset to A and there is no subset between them. So next one, singleton set B covers empty because empty is subset to B. But there is a set is there A, but empty is subset to A, but A does not subset to B. So that B covers empty. Next one, set A comma B does not covers singleton A, does not covers empty. You take empty because empty subset to AB, but there is a set empty subset to A does not A subset to AB. So there is a set in the middle. So it does not covers empty. Next one, singleton AB covers A. AB covers A because A subset to AB and but there is a condition failed. A does not subset to B even though B is subset to AB. So AB covers A. Next similarly A comma B covers B. So clearly B is subset to AB. So there is no other set in the middle. So this is a subset. Now divides. Y covers X means first condition X divides Y. Y covers X means X divides Y and no Z such that X divides Z and Z divides Y. So in divides relation, Y covers X, which means X divides Y, the first point, and there is no Z such that X divides Z and Z divides Y. So there is no type of Z here. Then only Y covers X. When you see one example, P is equal to 1, 2, 4, 8, and divides is the partial ordered relation. So it is a poset. Now we can check the covering conditions. 2 covers 1. So first you fix the first element, then from the next elements we can check which elements covers 1. So 2 covers 1. So clearly 2 covers 1 because 1 divides 2. 1 divides 2 and there is no other elements. 1 divides that element divides 2. There is no element. So that 2 covers 1. Next, 4 does not covers 1. 4 does not covers 1 because 1 divides 4, okay, but there is an element 2, 1 divides 2 and 2 divides 4. So there is an element 2 is there, 1 divides 2 and 2 divides 4. So that 4 does not covers 1. Similarly, 8 does not covers 1. Next, coming to the second element 2. Next, check the other elements. 4 covers 2. 4 covers 2 because 2 divides 4 and there is no other element such that 2 divides that element and that element divides 4. There is no element. So that 4 covers 2. 8 does not covers 2 because 2 divides 8, okay, and 2 divides 8, okay, but 2 divides 4 and 4 divides 8. There is an element 4 in this set such that 2 divides 4 and 4 divides 8. So 8 does not covers 2. And finally 8 covers 4 because 4 divides 8 and there is no other element such that 4 divides that element and that element divides 8. So that 8 covers. Okay. So next one, poset. So poset already we discussed here. A set together with a partially ordered relation on that set is called a poset. So here R is the partial ordered relation. So which means reflexive, antisymmetric and transitive. So next one is Hasse diagram. So Hasse diagram is a pictorial representation of representation of poset. Hasse diagram is a pictorial representation of poset is called Hasse diagram. So in this Hasse diagram, every element of P can be represented by small circles. Every element of P can be represented by small circles, and if x less than y and y covers x, if x less than y and y covers x, then write x is below y. X is below y. So which means x is below y. So we have to represent like this. So y covers x means, so y is drawn below x. So x is drawn below y. And y covers x means y and x are connected by a straight line. X and y are connected by a straight line. X and y are connected by a straight line. See, let us see some of the examples. So first example, P is equal to 1, 2, 3, 4 be the set, and we take the less than or equal to is the partial ordered relation. So clearly P comma less than or equal to is a poset. P comma less than or equal to is a poset. To draw the Hasse diagram, so we have to write the covering conditions, then Hasse diagram. We have to write the Hasse diagram. So covering conditions. So one side covering conditions, another side Hasse diagram. So first you fix the first element 1, then we check from the other elements which elements are covers the first element. So clearly 2 covers 1. So less than or equal to is the partial ordered relation. So 2 covers 1 because 1 less than 2 and there is no other element between 1 and 2. So 2 covers 1. And next one, 3 does not covers 1 because 1 less than 3 is okay, but 1 less than 2, 2 less than 3. So that 3 does not covers 1. Similarly, 4 does not covers 1 because there are 2 elements are there, 2 and 3, 1 less than 2, 2 less than 4. Similarly, 1 less than 3, 3 less than 4. So 4 does not covers 1. Coming to the next element 2. Next, 3 covers 2. 3 covers 2. 3 covers 2 because 2 less than 3, okay, but there is no other element between 2 and 3. So 3 covers 2. Next, 4 does not covers 3. There is an element 3 such that 2 less than 3, 3 less than 4. So 4 does not covers 2. Next, coming to the 3. 4 covers 3. 4 covers the clearly 3 less than 4 and there is no other element between 3 and 4. So these are the covering conditions. Now let us draw the Hasse diagram as 2 covers 1, which means 1 is drawn below 2. So 2 covers 1 is drawn below 2. So above element should be covering element, that is 2 covers 1. Next one, 3 covers 2. So 2 above element, which element covers 2? 3. So 3 covers 2. So this is the above element. Next, 4 covers 3. So 3 is drawn below 4. So we denote the numbers as a circles. Then using the covering conditions, 2 covers 1 means we have to draw a straight line from 2 to 1. And 3 covers 2 means we have to draw another straight line from 3 to 2. And 4 covers to 3, that means 4 to 3 there is an edge. So it is the required Hasse diagram for this set with the partial ordered relation. So next example, if we take capital A is equal to A comma B, then power set of A is equal to empty singleton A, singleton B, and A, that subset is a partial ordered relation on a set. So P of A comma subset is a partial ordered relation, is a poset, is a poset. So let us write the covering conditions one side and Hasse diagram is another side. So first we fix the element empty, then check the other elements. Which elements are covered? Empty. So clearly A, singleton A covers empty. Singleton A covers empty. because empty is subset to A and there is no other set such that empty is subset to that set and that set is subset to A. So A is covered empty. Next, B covers empty. So B covers empty because empty is subset to B, first condition. Second condition is there is a set A. Empty is subset to A, but A does not subset to B. So that B covers empty. Now AB does not covers empty because empty subset to A and singleton A subset to AB. Similarly, empty is subset to B and B is subset to AB. So AB does not covers empty. Now coming to A. Singleton B does not covers singleton A because initial condition failed. What is the initial condition? Subset. Singleton A does not subset to B. So initial condition is failed. So it does not covers. Next one, AB covers A. AB covers singleton A because singleton A subset to AB and there is no other subset in the middle. That means singleton A does not subset to singleton B even though B is subset to AB. Now coming to the next one, B, AB covers B. AB covers B because singleton B subset to AB and there is no other set such that this set is subset to that set and that set is subset to AB. So these are the required covering conditions. So now depending on the covering conditions we draw the Hasse diagram. So here we observe that two elements, two sets, these are not elements, these are sets, singleton A, singleton B are covering pi. So you take pi is the below element, above two elements we have to take singleton A and singleton B. Now AB covers these two elements. So that means the above element should be AB. AB covers singleton A and AB covers B. So that's why we have to write in the above. So now the depending on the covering condition we draw the straight lines. Singleton A covers empty. Singleton A covers empty and B covers empty and AB covers singleton A and AB covers B. So this is the required Hasse diagram. Now coming to the other example, third one, let us take P is equal to divisors of 12, 1, 2, 3, 4, 6, 12 and we take the relation as divides. So set of positive integers comma divides is always a poset, is a poset. Now we write the covering conditions. So covering condition and Hasse diagram is another side. So first we fix the first element. Now we can check for the remaining elements what type of elements covers the first element 1. So clearly 2 covers 1. 2 covers 1 because 1 divides 2. 1 divides 2 and there is no other element. 1 divides 2. There is no other element. 1 divides that number and that number divides 2. There is no other element. So that 2 covers 1. Next one. 3 covers 1. 3 covers 1 because the initial condition is 1 divides 3 is okay, but there is an element is there 2. 1 divides 2, but 2 does not divides 3. So, which is not there. So, it is not satisfied. So, that 3 covers 1. 3 covers 1. Next, 4 does not covers 1 because 1 divides 2 and 2 divides 4. There is an element 2 is there. There is an element 2 is there such that 1 divides 2 and 2 divides 4. So that 4 does not covers 1. Similarly, 6 does not covers 1. 12 does not covers 1. So next, coming to 2. 3 does not covers 2. The initial condition is failed because 2 does not divides 3. 2 does not divides 3. And then next one, 4 covers 2. 4 covers 2 because 2 divides 4 is the first condition, and then 2 does not divides 3 and 3 does not divides 4. So that 4 covers 6. Similarly, 6 covers 2 also. 6 covers 2 because first condition 2 divides 6 and there is no other element such that 2 divides that number divides 6. Here 4 is there, 2 divides 4 but 4 does not divides 6. 2 divides 4 but 4 does not divide 6. So that 6 covers 2. Next, 12 does not covers 2 because 2 divides 4 and 4 divides 12. So there is an element 4 is there. So that 12 does not covers 2. Next, coming to the third, 4 does not covers 3 because the initial condition is failed. 3 does not covers 3 does not divides 4. Next one, 6 covers 3. 6 covers 3. Clearly 3 divides 6 and 3 does not divides 4 and 4 does not divide 6. So 6 covers 3. Next one, 12 does not covers 3 because 3 divides 6 and 6 divides 12. There is an element like that. So that 12 does not covers 3. Next one, come to 4. 4, 6 does not covers 4 because initial condition failed. 4 does not divides 6. The next one is 12 covers 4. 12 covers 4 because the initial condition is satisfied. 4 divides 12 and 4 does not divide 6, even though 6 divides 12. So the condition is failed, so that 12 covers 4. The last condition is come to 6. 12 covers 6. So clearly 6 divides 12 and 6 divides, there is no other element such that 6 divides that number divides 12. So these are the covering conditions. Now we draw the Hasse diagram. So 2 above, right, 1 is the below element, 1 above elements are 2, 3. 2, 3. Now 2, 3, you observe 2, 3, there are 2 elements. So here 4 and 6, there are 2, 4 and 6. So these 2 elements covers 2 and 3. And you can write in the above 4 and 6. These are covering 2 and 3. The next one, 12 covers 4 and 6. So write 12 in the above of 4 and 6. Now using these conditions, we draw the straight lines. 2 covers 1, which means 2 to 1. Draw a straight line 2 to 1. 3 covers 1. Draw an edge from 3 to 1. 4 covers 2. 4 to 2. Draw. And 6 covers 2. You draw 6 to 2, an edge. And next one, 6 covers 3. You draw 6 to 3. Next one, 12 covers 4. You draw 12 covers 4. And next one, 12 covers 6. You draw 12 covers 6. So this is the required Hasse diagram for the divisibility. So this ends this lecture. Thank you.